All right, it says a regular pentagon is shown in the diagram below. If the pentagon is rotated around its center, the minimum number of degrees it must be rotated to carry the pentagon onto itself is, and then they give you possibilities here. So I think it might be good to look at maybe something simpler like a square.
hmm
And if
I
we, oh, sorry, go.
uh,
I didn't hear you. I apologize.
I did this one, and the way that I did it, it was like 360 divided by 5.
So it's whatever this angle
Okay.
is the answer. Because I was going to use the reference of this 90-degree angle here, because if you rotate a square onto itself, and now let's see, it's at clockwise. So if that 90 degrees down here, it's still on itself. Okay, now you have to first determine the number, you have to determine the total sum of the degrees, the sum of the interior angles. And this is a formula. This is the n minus 2 times 180, like that. And so in this problem, it's got 5 sides. 5 minus 2 is 540 is your sum. And then to find one angle there, we'll call that x. To find x, you have to take your sum and divide it by the number of sides. 540 divided by 5 is 108. So like when you said, okay, I'm going to use 360 divided by 5, that would be true if the total sum was 360. But for a pentagon, it is 540. I believe. Maybe I'm missing something here. I just like that we've got different answers for this. It also looks like question 2 is really similar. Trying to look at what's the difference between these. Needed to carry the pentagon onto itself. So there's the only language difference between 1 and 2 is the word carry versus rotated. And yet they've got yet another one here. Why is 3 exactly the same? This is very odd. Like the questions are okay. I take that back here. So maybe I am wrong. And there is this distinction between carry and rotated. Let me do some quick searching. Is that something you've been seeing in class?
Um, mhm. I took notes. I don't know if it was the same notes.
So I am seeing that some of these do show that it is what you said.
Yeah, that's what my notes say too.
Yeah, so I'm likely not correct on this one. I may be correct on the next one, but let me just look one more time. I guess I gotta spend a little more time looking at this question. So give me a moment here to just browse around, look for some things. Your class is one of the few that I've seen that actually emphasize this problem, these rotations so much. To carry the pentagon, onto itself. All right. So you're right. The answer is what you said. It is 360 divided by
5.
5. Yeah. But so is the answer for 2 and 3. and they're written really much like almost the same. Any idea where this came from? I mean, this is it's just so odd. Okay, well, I back up on this. This is not correct. It is 360 divided by 5, which is
72.
72. Yeah. It is also true that the second one is same thing, but it's written slightly differently. Maybe they meant a different shape. I don't know. Because it says say pentagon. It's just odd that you have 2 questions in a row that are exactly the same formula and answer. But this one is 360 divided by 5 again, or 72 degrees. Same with number 3. 3 is, yet another pentagon. This is yet another pentagon, n equals 5. Although this one, 1, 2, 3, 4, 5, angle of rotation. This one's different. This one is finally different. So this one it's still 360 divided by 5, which is 72. But you notice that answer isn't there, right? But every multiple of 72, so like every time you go 72 degrees, if you do that once, it's good, but you can do it twice. You could do 144. That's 72 plus 72. And then you could do it again, the 216. That's a third time. That's the 72 plus 72 plus 72. And that answer is there.
Yeah.
Is that okay? I guess. All right. So it's a pretty simple formula. You take 360 divided by the number of sides. That should help you to answer number 4. But again, kind of like number 3, the answer it's not just there. It's not just explicitly right there. There's a bit more to do. So here it says a regular hexagon is rotated about its center, which will carry the regular hexagon onto itself. All right, so again, it's 360 divided by 6, which is 60. But notice those aren't there, so you add another 60, 120, and that one is there. All right, you ready to do number 5? 5 here.
Yeah.
Okay, so this one's a decagon, and you have to know how many sides are in a decagon. A decagon has n equals 10 sides. So that means it's going to be the 360 divided by 10, or 36. So this one, there is another path to doing this. You could take each answer and divide it by 36, and one of them should work out perfectly, meaning a whole number. Or you can do like we've been doing and just start, keep adding them on there. But one of these will work out pretty well. If you have a calculator handy, I would encourage you to try that, or if you know the answer already, just let me know.
4.
Yes. Very good. All right, number 6. All right. So this is a much harder problem. It's a backwards problem. So this time they're not giving you the number of degrees. They're telling you it's n. So what they're saying is 360 divided by some number, we'll call it x equals n. Okay, so like for example, we know that x could be 3 because it's that would be a triangle. X equals 4 is for a square, x equals 5 is for a pentagon, and so on. So what you're trying to figure out here is like basically they're giving you, these are all values of n. So it's essentially like saying 360 over x equals 10. 360 over x equals 150. 360 over x equals 225. So one of these will work. One of these will produce a whole number. Any idea how to figure that out based on that description? Okay, so the other way to go here is when you have this is called a literal equation, is you solve for x. Okay, so to do that, you're going to cross multiply here. 360 equals x times n, and then you're going to divide both sides by n. Okay, so this is your formula. This literal formula now helps you to know what to try. So you're gonna basically divide each of these by, or 360 divided by each number, that's 36. 360 divided by 150, that's something. It's not a whole number. Same with this next one. It's not a whole number. 360 divided by 252, it's not a whole number. So the answer is 10. Just to kind of like full picture, going back to like the beginning here. This problem is like saying that you have a 36-sided polygon. Okay, what would you rotate by?
What was the question?
If it's a 36-sided polygon, what would you rotate by? And you already know from previous problems, it's always 360 divided by the number of sides.
10.
10, yeah. All right, let's look at number 7. So again, the formula is and I don't like this n degrees, but it's always like 360 degrees divided by the number of sides equals the angle of rotation. That's the formula. You have to say, okay, 360 divided by number of sides, angle of rotation. Now, they're telling you here that the angle of rotation is 36 degrees. Which regular polygon has a minimum rotation of 36 degrees?
Decagon.
Well, yeah, so it's like the answer to your question, you're like, or to answer this, it's 360 divided by what gives you 36, and it is 10, and that's a decagon. So similarly, for number 8, it's kind of the same problem, but with different numbers. So it's 360 divided by some number of sides equals 45. And an octagon has 8 sides, decagon has 10 sides, hexagon has 6 sides, and pentagon has 5 sides. So you have to also know which what side lengths go with which.
Mm, pentagon.
Okay, so if it's a pentagon, then 360 divided by 5 would equal 45. Is that true?
Um,
So no, that one's probably out.
mm, no. Oh, octagon.
Yeah, it looks like an octagon. 360 divided by 8 is 45. Good. Right. Next page here. All right, so number 9 here. It says which figure always has exactly 4 lines of reflection that map the figure onto itself. Okay. Sometimes it's easier to like eliminate unless you already know the answer. But let's look at a square first. So what I take them to mean by the square is, for example, there's this line that goes right down the middle that reflects it. So that's 1. Then this line also reflects it.
No.
And then there's a diagonal. And then there's another diagonal. So that's 1, 2, 3, 4.
So it's a square.
It would appear to be a square. Like I'm sort of wondering, well, why doesn't it work for a rectangle? I'm just sort of curious off to the side here. Actually, let me draw that differently. Let's see here. Because this one feels like it's going to have a lot of the same ones. It's going to have the vertical, the horizontal, and then it's got this one, and then this one. So why is it not a rectangle? That's what I'm sort of wondering here. Thankfully, well, there must be another one that works for a rectangle, but I'm not seeing. I'm not seeing. So you might ask your instructor about this one. Say, hey, I was working through this. Rectangle sure looks like a square. The octagon's going to have a lot more. I don't know if you want us to draw that, but it's got way too many symmetries for it. I don't even know if I've drawn this one that well. Not really. It's got the obvious ones that go up and down, but it's also got them through each of the vertices. Like that as well. So it's obviously got a few more than that. So there's some relationship, and this is covered in like Euclidean geometry. It's which is an really advanced math class, but there's some relationship between vertices and probably these lines of reflection. Okay. Have you tried like number 10 yet?
Number 10. No.
Okay. This is kind of like some of that delta math we've been doing. Which transformation would not carry a square onto itself? So if this were a standardized test, I don't know if you've had any interest in the SAT prep class, but you always sort of start from the bottom up when you're doing these on time tests, because it's usually the case that they want you to go through all of them and not not waste time by going through them rather than starting from the bottom. But you don't have to do that here. I mean, we got plenty of time, but a reflection over one of its diagonals, well, obviously that is okay. Excuse me. Like if it both rotate over its diagonals, you're going to get back to the original. A 90-degree rotation about its center. So that's really the key point there, is about its center. If you rotate about its center, you will get back to where you started. 3 is different though. 3 is a rotation about one of its vertices. So let's say you rotate about this vertice right here, and they don't even specify whether it's clockwise or counterclockwise. It doesn't matter because you get to the same place, but you're either going to get down here going clockwise or down here for counterclockwise. And that obviously does not carry it onto itself. Number 4. So a perpendicular bisector, remember it's got to cut it in half. So that's like this one, where it's completely cut in half.
Okay.
And that one is okay. All right, so number 11, got a rhombus here. So which transformation would carry the rhombus onto itself? And so that, like, whenever you're looking at the origin, if that's like, if it were this point, I guess, in red, which is not the origin, then it would be okay. Like that center point is okay. It's when it's the origin is not at the center. The origin's actually, move down here. That's not okay. It's not going to mirror about its rotate about itself. So that one's out. The next one here, this line y equals 1/2 x plus 1. So that, goes through 1. It's got a slope of up 1 over 2, up 1 over 2. That one's looking pretty good to my eye. What do you think? There, I'm also going to say that I know for sure that the last one is going to work, because x equals 0 is right here.
Yeah.
And I know that one works, but why doesn't this 1/2 x plus 1 work?
Um.
I'm sort of asking rhetorically, I guess, because I'm not sure why it doesn't work. Let me check here, see if there's any more information. It does say that the only answer is 4 for this, but I guess I'd want to know why that doesn't work. Because it sure looks like it works. Like it looks like it cuts it pretty much in half. I know the line isn't drawn great, but it's parallel to this other one. It's parallel, like the blue lines. They're all parallel to the black lines on the edges there. I don't know. What do you think?
I think it's 4.
It probably is. I would love an explanation why, though. because it sure appears to have the right look. I know I should know the answer, but I just don't. I couldn't tell you. All right, number 12. It says this is one of those would nots. Those are always really tough, would nots. So the thing that's probably not seen very clearly from the picture is that there is a longer versus a shorter diagonal in this drawing. Sometimes it's easier to see when you exaggerate it a bit more. So if you push the house over, or the rectangle over, and you get something like, it's a little more, you find that the one here that's in red is the longest. So this is the longer diagonal here.
Mhm.
All right, and then so you're really looking for like congruences in this case. So like this side is congruent to this side, but the diagonals do bisect each other. So it's going to be down, it's going to come down to one or two basically in these situations, like, because like one of the reflections is okay, but the other isn't. Why is that? Sort of an odd thing here. Maybe they actually both work. Maybe I'm looking at something else, because they do seem like they're congruent, these triangles. Let me grab the right color here. Like this one on the lower right looks to be the same as this top left. And then if you were to copy it and kind of say, okay, now let me look at it from the other direction. These actually look like they're okay, meaning that the ones on the left and the right. So one and two are probably okay. So a clockwise rotation 90 degrees about the intersection of diagonals. It's not quite the center. That's the problem here, is that this isn't the center anymore. Like the center was here, but then when you push it, it kind of pushes it up. And I'm not sure that that's exactly in the center. So the 180 though, the 180 is like a full, this top becomes the bottom, the left becomes the right. That looks okay. But the 90 degrees would make sort of it, I don't know, almost kind of, it would look at, if this goes 90 degrees clockwise, it ends up and almost looking like this. I know it's not drawn very well. But the idea is that it doesn't look the same. So that's why 3 is the right answer. Is there anything else you want us to work on today? Because I mean, it's obviously not very exciting, very interesting. Is there anything else we could spend some time on that would be more helpful to you than going through this? Or is this it?
This is it.
This is it. Okay. So I think the main takeaway for a rhombus is that you have to rotate it a full 180, or you get something that is, and you could almost like use your paper on the exam, like fold it up into something and rotate it, or 90 degrees versus 180, and see if it looks the same.
Okay.
All right, so let's keep going here. So the next one is it's about a square graphed in the plane. A lot of effort went into making these questions. These are nice questions. All right, again, one of these which does not carry. That means there's going to be 3 that work and 1 that doesn't. So you almost want to draw the ones that work, like this one here. This is x equals 2. I guess that's not on there. Y equals 2. So that one works. So we're looking for ones to get rid of. That one's out. The line y equals x. is going through the origin. That one looks good. So that's gonna make it out. And then it may be obvious now which is the correct answer, which isn't, but let's keep going here with, so x equals 5 is going to hit on this right edge, and that's kind of a big, a big indicator. No, that will not work. The last line, the y plus x plus y equals 4, that one actually is going to go through the other diagonal. It starts at 4, has a slope of -1. And sorry, it does not quite go through. Wait a second. X 1, 2, 3. Okay, I graphed it in the wrong spot. So I just waiting for my screen to allow me to change that. So it does in fact go through that other diagonal. So that's why that one is out, and the correct answer is x equals 5, because that's this line right over here. So it would flip and obviously not be the same.
Mm-hmm.
All right, 14. Look at 14 now. All right, why don't you try this one, or if you already have an answer, we can look at it together. If you got the paper there in front of you still, I would try drawing some of these lines, or drawing the the axes, seeing if that does or does not work. I think you'll find the answer pretty quickly, though.
Reflection over the y-axis.
Yeah, so that one would make it look like, at the right number of squares, it would look something like that when it's done. So yeah, that is it. Good. Let's have you try number 15. I'm going to snip that in.
Rotation of 180 about the origin.
Yeah, so like that origin that's the key there, because if you do it about the other point, the other point's right in the center of it. And that one's okay, because whenever you rotate about the point in the center, if it's got all that symmetry about it, then you're good. So yeah. Very good. All right, down to the last couple. Let's see here. All right, why don't you give this one a try, please? This is one of the will nots. So there's 3 that work and one that does not.
Three.
So 6, 6. We got to find that point. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So that point is not in the center. So that will definitely not work. 5, 5 though is. That's why it's so important to, get that one there. So yeah, so your answer is number 3. Good. All right, next problem here. Okay, which transformation carries the parallelogram below onto itself? One of the things I do notice here, the kind of the symmetry of the points, the fact that they're just switched signs. That's key here. to notice. So this one, y equals x is this line right here. That's one possibility. And the other one is y equals minus x. Counterclockwise 90. So 90 degrees is always kind of the dangerous one when it's this pushed over shape, because that tends to, fold it in the opposite direction. It would look something like this when it's done.
Is it 4?
It sure looks like it. Again, kind of like wondering why there's not multiple answers here. This one does look like it is 4, though. There must be something about this length not being, but it is the same. I don't know. Sometimes else. It's okay. I guess I do have the answer. It's because this length right here is not the same as the one going the other way. Like that length right there. Let me actually get it. Is 6. Well, that's 6 as well. But I believe we know the answer for sure is A. But I've got some concerns why it's not one of those other ones. I guess I couldn't tell you for sure. Okay, last question here. 18. This is kind of like the ones we were starting out with, the carry onto itself. So hexagon here, 6 sides, counterclockwise about its center. Minimum number of degrees rotation will coincide with itself. So that's the 360 divided by n again, where n is the number of sides. So this one is 360 divided by 6, 60 degrees.
Okay.
All right. Well, if that is all you wanted to work on today, we've done it. Are you okay for us to stop here?
Yeah.
All right. I will stop the recording.